Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 2 on dilations in the coordinate plane. In our last lesson, we introduced the idea of a dilation, which hopefully was a little bit of review from middle school math. Dilations are interesting geometric transformations because what they are doing is they're taking a geometric object and they're stretching it away from or collapsing it towards some center point. So let's get into it and review some of the basics about dilations. Now, in our last lesson, we looked at major dilation properties, okay? So let's take a look at those. Number one, a dilation will map a line not passing through the dilation center to another parallel line. So let's take a look at that one really quickly, right? In other words, when I have a dilation that's centered at point C, all right, and I'm dilating point A, right? I draw that ray through C, starting at C through A, right? And then I stretch A prime away from A or shrink it towards C, right? And I do the same for some other point B that's on line AB. The image line that's produced, A prime, B prime, always will end up being parallel to line AB. All right, so that's property number one. Property number two, which isn't nearly as interesting, a dilation maps a line passing through the dilation center to the same line. All right, and let's talk about this one a little bit as well, right? So if I've got some line AB here, and the center of dilation lies on the line itself, then when I stretch, let's say, A prime out this way and B prime out that way, I'm simply still getting the same line. Now, the final piece, number three, concerns mapping a line segment. A dilation maps a line segment to another line segment whose length has been scaled by the same scaling factor as the scale constant for a dilation. And again, this is kind of interesting because when we dilate a line segment, let's talk about like segment AB, right, from A to B. We're really stretching A out by some scaling factor and B out by the same scaling factor, and yet that means that A prime, B prime will be scaled by exactly the same factor as what we scaled the two individual endpoints by. And that's not necessarily obvious, right? If we increase the distance that A is away from C by twice, and the distance B is away from C by twice, let's say, it doesn't always stand to reason that the segment that we will get will be twice as long as our pre-image segment. But that's absolutely true. Again, the first point here and the third point really are the most important. We will have to deal with this situation every once in a while, but it's not nearly as important as 1 and 3. All right, so now let's start to take a look at dilations in the coordinate plane, and let's take a look at them first in exercise number 1. 3 points have been plotted on the grid below. Find and plot their images after a dilation centered at the origin with a scale factor equal to 2. All right, so before we kind of like launch into the more difficult one, which is the point 3, 4, more difficult one in quotes, all right, let's think about some easy ones, point A and point B, which lie on the X and the Y axis respectively. Now, this should be an easy idea, right? We've got our origin here at 0, 0. And of course, if I'm going to dilate point A, just by what a dilation is, I would be drawing a ray through the origin and through point A, right? And A prime, the image of A, will lie somewhere along that ray. Now, if my scaling factor is equal to 2, A right now sits 4 units away from the origin, right? So its image will then have to sit 8 units away from the origin, and not surprisingly, that means that point A prime is at 8, 0. Now this would be different again if we were talking about something that wasn't centered at the origin, but it seems perfectly obvious that if A, which is at 4, 0, ends up being twice as far from the origin, then it must be at 8, 0. And of course, likewise, we can do the same for B. Right now, B is 2 units away from the origin, and if I stretch it to be double that length, right, it will then end up being down here at B prime, which will then be at 0, -4. Now the trickiest one by far in this situation, because it doesn't lie on either the x or the y axis, is point C. But again, keep in mind, right, the fundamental idea of a dilation, right? The fundamental idea of a dilation is that I would end up, if I'm trying to dilate this, right, I'm going to end up having a ray that passes through the origin, all right, and the point that I'm dilating. My image point must lie somewhere on here, right? Now, where does it lie? Well, right now, if I were to go from the origin to point C, I would have to go 3 units to the right and 4 units up. If I go another 3 units to the right and another 4 units up, it stands to reason that C prime would now be at 6, 8. Okay? And that's it, right? That's where C prime ends up being. And of course, it makes sense that this distance and this distance would be the same. They're the hypotenuse, right, of 2 right triangles that are congruent. Let's take a look at letter B just to verify that we did C prime correctly. Exercise number 2. Verify that C prime is twice the distance from the origin that C is. All right, so this is easy enough. We can just do this using the distance formula or using the Pythagorean theorem, either way, right? We've got the origin, O, at 0, 0. We've got C, which is at 3, 4. And we've got C prime, which we believe is at 6, 8. Okay? If I want to verify that C prime lies twice the distance that C does from the origin, I just need to use the distance formula, right? So I'm going to say OC, right, which is the distance from the origin to C, would be 3 minus 0 squared plus 4 minus 0 squared, which is just 3 squared, 9, 4 squared, 16, and that would be the square root of 25, which would be a distance of 5. On the other hand, the distance from the origin to C prime, OC prime, right, would be 6 minus 0 squared plus 8 minus 0 squared, which would be equal to 36 plus 64. I got to get rid of my ruler here, which is the square root of 100, and that's equal to 10. So it appears that OC prime is in fact twice OC, right? And that's kind of what we wanted. Now what this leads us to is a very, very nice conclusion, all right, which is the algebraic rule for dilations. Dilations in the coordinate plane where the center's at the origin are extremely common. Thankfully, their algebraic rule is very simple, so let's take a look at it. Dilations centered at the origin. A dilation in the coordinate plane that has a center at the origin, and that's very key, and a scale factor of k, will map the point x, y as x, y goes to k times x, k times y. And that's exactly what we saw in the last problem, right? Let's go back to this, right? With a scaling factor of 2, when I wanted to map a at 4, 0, I just multiply 4 by 2, I multiply 0 by 2, and I get 8, 0. Likewise, 0, negative 4, and the most important one, right? C of 3, 4, the 3 became 6, the 4 became 8, and I got a point that was twice as far from the origin as the one that started with, as the pre-image. All right, so algebraic rule for dilations centered at the origin are simple if you're in the coordinate plane, which we won't always be working in the coordinate plane, but boy, when we are, these dilations are pretty easy. Let's take a look at exercise number 3. A line segment has endpoints at A, 2, negative 4, and B, 8, 4. It is first mapped to segment A prime, B prime by a reflection across the line y equals x, and then dilated with a center at the origin and a scale factor of 3/2 to produce segment A double prime, B double prime. Letter A. Find the coordinates of A double prime and B double prime. Show the mappings below. All right, well, let's do A together, right? And what we're going to be doing is we're going to be putting it through 2 transformations. The first one is a reflection across the line y equals x, and the second one then is a dilation with the center at the origin and a scale factor of 3/2. So here's how we go, right? We've got A, which is at 2, negative 4. All right, and that's going to go to A prime. And recall, the rule for reflection across the line y equals x is simply switching the x and the y coordinates. So that's just our first transformation. 2, -4 gets mapped to -4, 2. Now the dilation, right, now I'm going to take A prime at -4, 2, and I'm going to map it to A double prime, which will be -4 times 3/2, 2 times 3/2. If you absolutely have to, break out your calculator for that, but of course -4 times 3/2 will be -6, and 2 times 3/2 will be 3. So our final image point for A double prime is -6, 3. What I'd like you to do now is figure out the final coordinate points for B double prime. All right, let's do it. I think I'm going to extend my page a little bit here. So we've got, where is my coordinate B? There it is. B, which is at 8, 4, right? We'll first map that to B prime, which will be 4, 8, that reflection across y equals x. And then B prime at 4, 8 will get mapped to B double prime, which will be 4 times 3/2, 8 times 3/2. Again, a little cross cancellation. And we'll find that B prime is at 6, 12. I'm sorry, that's B double prime. All right, so A double prime is at -6, 3. B double prime is at 6, 12. Let's take a look at letter B. The length of segment AB is 10. What is the length of segment A double prime, B double prime? Well, look, the straightforward way of doing this is, of course, by using the distance formula and simply calculating the length of A double prime, B double prime by finding the distance between these 2 points. But we can actually do it a little bit easier, all right? Pause the video now and see if you can think about a way to calculate the length of A double prime, B double prime without having to use the distance formula. All right, well, it's relatively simple. And first, I just want to suggest that, of course, A prime, B prime is the same as AB, and that's 10. All right, in other words, the length of that intermediate segment, right, that segment A prime, B prime, is the same as the length of segment AB because a reflection is a rigid motion, and rigid motions don't change lengths. Now, A double prime, B double prime has to be K, my scaling constant, times the length of A prime, B prime. Right? That's one of the fundamental properties of all dilations, which is the length of a segment, of an image segment under a dilation, will be the length of the pre-image times that scaling constant. So I can say that the length of A double prime, B double prime is 3/2 times 10, which must be a length of 15. And that's most certainly what you would get if you went through the distance calculation between B double prime and A double prime. But this is quicker. All we have to do is multiply that 10 by 3/2. Okay, let's keep working with dilations in the coordinate plane. Fundamental properties of dilations. Now that we know how to dilate points in the coordinate plane, we can examine and verify the fundamental properties of dilations. So let's take a look at those in exercise number 4. A segment has been plotted below with endpoints at A, -1, 4, and B, 4, 2. Letter A, plot segment A prime, B prime, the image of segment AB, after a dilation with the center at the origin and a scale factor of 3. Show the mapping of the endpoints below. All right, well, I think we've done enough of these at this point that it should be pretty easy. Why don't you go ahead and just do letter A? All right, well, the first thing that I'm going to do is actually just come up with those coordinates. So A, which is at -1, 4, will end up going to A prime, and I'm just going to multiply both of those coordinates by 3, negative 3 comma 12. B, which is at 4 comma 2, will get mapped to B prime, which will be 12 comma 6. All right, so let me just plot those. Negative 3, 12. And 12 comma 6. A prime, B prime. Now I can draw it in my segment, assuming that my graph grid doesn't shift on me, which it just did a little bit. Let's see if I can lock that down so that doesn't happen again. All right. And there we have it. All right. Now, real quick, even though there's absolutely no need to do this, I kind of like drawing this picture right now because I keep wanting to remind you the basic idea of dilations, which is that B and B prime should lie on a common ray that starts at the origin, right? And it does. And A prime should lie, whoops, on a constant ray that lies at the origin. That doesn't seem quite right. Oh, that's because I was at negative 2 instead of negative 3. Well, that's a good thing, I suppose, that I did that then. Let's try this again. Negative 3, 12. Boy, me and my coordinate geometry. All right, let's get that segment back in there. What a good check that was. Like, why doesn't this actually line up? All right, let's try this again. Now it looks good. All right. Again, the image point for any dilation, don't forget this, right? The image point for any dilation should always end up lying along a ray that starts at the center of the dilation, passes through the pre-image point, right? Let me go ahead and label that. Okay, now we've got it, right? And this picture is something you see time and time and time again with dilation work. And by this picture, what I mean is sort of a larger triangle and then a smaller triangle within it, both of which share the center of dilation as the vertex angle, if you will. Okay, now that we have all of that, let's take a look at letter B. Find the slope of AB and the slope of A prime B prime in simplest form. What do these slopes tell you about the two segments? Okay, great. So before we kind of move this up, let me get down the 2 or the 4 points. That way we have them here and it's easier to calculate the slopes. All right, let's do it. Here, I'll take the easy one, as I always do in these problems. Let's do the slope of AB together and then have you do the slope of A prime B prime on your own. Here we go, right? So the slope of AB is going to be the change in y, 2 minus 4, divided by the change in x, 4 minus negative 1. All right, that's going to be negative 2/5, and there's really nothing I can do to reduce that. Negative 2/5. All right, why don't you go ahead and calculate the slope of A prime B prime, and then once you've reduced it, see if you can make a conclusion based on the two slopes. All right, let's do it. So in the case of segment A prime B prime, again, we've got the change in y, which is 6 minus 12, divided by the change in x, which is 12 minus negative 3. That's going to be negative 6 divided by 15. And now I can divide both the numerator and the denominator by 3, right, to reduce this fraction, and I'll get negative 2/5. So the slopes of both of these two segments are the same. And of course, what that tells us immediately through coordinate geometry is that AB is parallel to A prime B prime, right? And that was one of our major conclusions, or one of our major properties about dilations, which is when we dilate, right, a segment whose center is not lying on that segment, then our image segment ends up being parallel to the pre-image segment. And you can probably see that in the picture. They look parallel to one another, but the slopes nail it down, right? They give us that definite evidence. All right, so letter C, let's take a look at that. Find the lengths of segment AB and segment A prime B prime in simplest radical form. Show that A prime B prime is equal to 3 times AB. Okay, cool. So let me again kind of just write these points down. It'll make my life easier. A at -1, 4, B at 4, 2, A prime at -3, 12, and B prime at 12, 12, 6. All right. Now, if we want to find lengths, we always are using the distance formula. So, why don't you go ahead and find the length of AB, we'll reverse roles here, and then together we'll find the length of A prime, B prime. Go ahead and do that. All right, let's do the distance formula. So the length of AB, right, will be the square root of 4 minus -1 squared plus 2 minus 4 squared. 4 minus -1 is 5. And 2 minus 4 is -2. So AB will be the square root of 25 plus 4, which is the square root of 29. Now 29 is a prime number, and therefore there are no perfect squares that are divisors of 29 other than the number 1. So we cannot simplify the square root of 29 any more than it already is. Now let's do the segment A prime, B prime together. Let's find its length together. Now remember, what we're hoping for here is that the length of segment A prime, B prime is 3 times the length of segment AB. So let's take a look and see if that's actually the case. All right, so A prime, B prime equals the square root of 12 minus -3 squared plus 6 minus 12 squared. A prime, B prime is going to be equal to the square root of 15 squared plus -6 squared. A prime, B prime is going to be 225 plus 36. I think. Is it 225, 15 squared, Joey?
261.
Well, the final answer. Yes. Yeah. So 225. Yes. Okay.
Yes, that's right.
Great. Square root of 261. I just wanted to make sure. Now, in one case, right, we've got the length of AB, which is the square root of 29. And in the other case, we have the length of A prime, B prime, which is 261. Somehow, I want to justify that this is 3 times this. Well, this one we can actually simplify. And in fact, we can break down the square root of 261 into the square root of 9 times the square root of 29. So if you play around with your calculator, which apparently I don't have out right now, but if you play around with your calculator, what you'll find is that the biggest perfect square that divides into 261 is 9. So just like we always do when we simplify square roots, A prime, B prime now can be written as the square root of 9 times the square root of 29, in which case, whoops, boy, that's looking less and less like an A as I draw it. A prime, B prime is equal to 3 times the square root of 29. And there it is, right? AB is equal to the square root of 29. A prime, B prime is 3 times the square root of 29. So A prime, B prime is 3 times AB. In other words, the length of the segment, right, got scaled by exactly the same amount as what the individual endpoints got scaled by. All right, therefore, right, justifying that third property of dilations. Let's keep going. One more problem. Now we want to take a look at dilating entire lines. So in the last problem, we were just dilating a segment. But let's take a look at dilating an entire line. Sometimes we want to dilate all the points along a line and produce the equation of the image line. Let's take a look at that in exercise number 5. Line M is shown plotted on the grid below along with 2 points marked on its graph. Letter A, give the equation for line M in slope-intercept form. All right, so I'd like you to pause the video right now and just tell me what the equation of that line is in y equals mx plus b form. All right, this should be a piece of cake, right? Slope-intercept form, right? That's the one that you've been working with for years as opposed to the point-slope form, right? We can just look at this, right? The y-intercept is 2. The slope, that's simple. We go over 3 and up 2, so the slope is 2/3, in which case y equals 2/3 x plus 2. There we go. That doesn't really look like an x. Let me make it look a little bit better. Y equals 2/3 x plus 2. Simple. Nothing to do with dilations. All right, letter B. If line M is dilated with a center at the origin and a scale factor of 2, plot the image line on the grid. Show where each of the 2 marked points gets mapped under this dilation. All right, so the easiest way to dilate an entire line is to honestly pick any 2 points on the line, any 2 points on the line whatsoever, dilate them both with whatever scale factor they give you, and then draw a line through those 2 points. So for instance, we have the point 0, 2, right, the y-intercept. And under this dilation, that will go to the point 0, 4. Likewise, we have the point 3, 4. And under this dilation, that'll go to the point 6, 8. Right, so I don't need to dilate every point, I just need to dilate a couple points. And now, let me get rid of all of this. That will then be this point, and 6, 8. This point, in which case, my new line is going to look something like this. There it is. All right, so that's our image line. Now, letter C. What is the equation of the image line? All right, well, we already did one once. Try to come up with the equation of the image line. Now, what is hopefully simple to see, very, very simple to see, is that these 2 lines are parallel. So of course they must have the same slope. If you really wanted to, you could use these 2 points and actually do the slope calculation. But ultimately, you're going to get a slope of 2/3. That's what you're going to end up having. The only real question is what the y-intercept is. But that's simple, right? The y-intercept is 4. And that is simply the scaled version of this y-intercept, right? The y-intercept here that was at 2 became a y-intercept of 4. What the y-intercept is, truly, is the distance and direction, but the distance that that point is on the y-axis away from the origin. So that y-intercept will get scaled by whatever the scaling factor is, but the slope, of course, remains the same because the image line is parallel to the original line, right? So we just end up having y equals 2/3 x plus 4. Again, notice, right, same slope due to that parallelism, but then a scaled y-intercept. Again, makes sense, right? The y-intercept must get farther from the origin or closer to the origin, all based on what the scale factor is. If our original y-intercept had been -5, our scaled y-intercept would have to be -10. All right, that's just the way it works because every point will be twice as far from the origin as the original point. The interesting part is, of course, that the slope doesn't change. We get a parallel line for its image. Now, one last question before we summarize this particular lesson. Letter D. If line M is dilated by a factor of 2, using the point 3, 4 as a center instead of the origin, explain why the image line would have the same equation as line M. All right, cool. So why don't you think about this a little bit? Pause the video now. Well, the real key is where the center of this line is. If 3, 4 is the center, if this point is now the center, well, as we discussed right at the beginning, or as we reviewed right at the beginning, right, if the center lies on the line that you're dilating, you get the same line, right? So it would have the same equation, and the reason is because the center of dilation lies on the line you are dilating. And it's kind of cool, really, right? If it was a line segment, the line segment would get longer or shorter or whatever. But the idea here is just think about this. If I've got a point right here that's my center, right, and I took some other point, I would just stretch it away, but still along that same direction of the line so that it was twice as far from the center. And likewise this way. But we'd still get the same set of lines because we would just be stretching that line, right, in its own direction. All right, so let's summarize, right? Today what we did is we took what we saw in our last lesson on dilations, but then we put it in the coordinate plane. And we saw one of the nicest things, which is that if we're in the coordinate plane and our center of dilation is at the origin, which most often it is, not always, but most often it is, then what happens is that to dilate a given point by a given scale factor, you simply multiply both the x and the y coordinates by that scale factor. The cool thing about this is that we can then verify those various properties of dilations in the coordinate plane. We can see them. We can see that when we dilate a line or a line segment, using a point as its center that doesn't lie on that line, then we get an image that is parallel to the original. Very important. And if we're dilating a line segment, we get our image line segment to have a length that is scaled exactly by the same constant as what the original scaling factor was. Okay? The only exception to all of that is if you end up dilating a line or line segment where the center lies on the line or line segment that you're dilating. Then you essentially just get the same line. All right, we're going to work with more of this as we work through Unit 7 because dilations are laying the foundation for everything in Unit 7. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.